Somewhere past the edge of our entire solar system, a NASA spacecraft has been quietly picking up a constant, low monotone signal, a genuine physical frequency, generated by nothing except the empty space between the stars itself. Before we go further, one quick correction, because it matters for getting this story right. The famous version of this discovery actually belongs to Voyager 1, not Voyager 2, and I'll explain exactly why that distinction matters in a minute. But Voyager 2 has its own genuinely fascinating part in the same story, one that doesn't get nearly as much attention. Stick around, because I'm about to walk you through exactly what this frequency is, how scientists detected it, and what both Voyager spacecraft have actually confirmed about the sound of interstellar space. And hit subscribe now, because this channel breaks down real published research without the exaggeration, and you do not want to miss where this story goes next. To understand what this frequency actually is, and why it counts as a genuine scientific discovery rather than science fiction, you first have to understand what happens the moment a spacecraft crosses out of our solar system entirely. It also helps to understand that the instrument responsible for all of this wasn't originally built with interstellar space in mind at all. The plasma wave instruments carried on both Voyager spacecraft were designed back in the 1970s primarily to study the planets they were scheduled to fly past, and they proved their worth almost immediately. During Voyager 1's flyby of Jupiter in 1979, that same instrument detected the electromagnetic signature of actual lightning strikes occurring within Jupiter's turbulent atmosphere, a genuinely unexpected discovery at the time. The same basic hardware went on to study the solar wind, gradually thinning out as both spacecraft traveled farther from the Sun, long before anyone on the mission team could have known that. Decades later, that exact same equipment would end up detecting the ambient hum of the material filling the space between the stars themselves. It's a reminder that some of the most significant scientific findings in this entire mission came from instruments doing a job their original designers never specifically planned for, simply because the spacecraft carrying them managed to survive long enough to reach somewhere nobody had built equipment to study before. Voyager 1 crossed the heliopause, the boundary separating the Sun's zone of influence from true interstellar space, in August of 2012. Voyager 2 followed the same milestone in November of 2018, crossing at a completely different location. Years later, and in a different direction from the Sun. Once either spacecraft passes that boundary, it stops swimming through the solar wind, the outward stream of charged particles constantly blown off by our own Sun, and instead starts swimming through an entirely different kind of material, the sparse, cold plasma that fills the vast space between stars, sometimes called the interstellar medium. Both spacecraft carry a plasma wave instrument, originally designed decades ago to study exactly this kind of ionized gas, and both have continued using that instrument ever since crossing into this genuinely new environment. Here's exactly where the real story diverges from the version implied by a title like this one, and it's worth being upfront about it. The initial, and still by far the more famous, discovery of a persistent frequency in interstellar space came from Voyager 1, not Voyager 2. In 2013, physicist Don Gurnett at the University of Iowa and his team used Voyager 1's plasma wave instrument to detect a burst of oscillations at a very specific frequency, roughly 6 kilohertz, triggered by a shock wave from the Sun rippling through the surrounding interstellar plasma. That frequency corresponded almost exactly to the plasma density scientists expected to find in true interstellar space, and it became one of the key pieces of evidence confirming Voyager 1 had genuinely left the solar system. But that initial detection depended on a lucky event, a solar shockwave happening to pass by at the right time to excite that oscillation in the first place. It wasn't yet a constant, always-on signal. If you're the kind of person who wants space stories explained clearly instead of buried under jargon, go ahead and drop a like on this video right now, because it genuinely helps this kind of content reach more people who would enjoy it. That changed in 2021 when Cornell University doctoral student Stella Koch-Ocker, working with astronomers including Cornell's James Cordes and Shami Chatterjee, went back through 5 years of Voyager 1's transmission data, searching specifically for something quieter and steadier than those dramatic shock-triggered bursts. According to their findings, published in the journal Nature Astronomy, they found exactly that. A faint, narrow-frequency emission running essentially continuously in the background, distinct from the broader, more chaotic vibrations produced by solar shockwaves. Ocker described the signal in comments at the time as very faint and monotone, precisely because it sits within such a narrow frequency bandwidth, and researchers began referring to it informally as the hum of interstellar space, or sometimes, more poetically, comparing its steady, gentle character to the sound of light rain. According to Chatterjee, this discovery mattered enormously for a very practical reason. Before finding this persistent hum, researchers had no reliable way to continuously track the density of the plasma. surrounding Voyager 1 unless a solar shock wave happened to pass through and briefly excite a detectable oscillation, an unpredictable, occasional event rather than a steady stream of data. With this newly identified persistent emission, Voyager could instead continuously report back exactly what density of interstellar plasma it was moving through, moment to moment, regardless of whether the Sun happened to be sending any disturbances outward at that particular time. In Chatterjee's own words from Cornell's public statement on the discovery, the spacecraft was essentially able to keep saying, here's the density I'm swimming through right now, and here it is now, and here it is now, a continuous readout rather than an occasional snapshot. It's worth being precise about what actually generates this frequency, because it isn't some exotic, otherworldly transmission. According to the researchers involved, the leading explanation is that this persistent hum comes from the natural thermal jitter of electrons within the interstellar plasma itself, tiny, constant oscillations that arise simply from the basic physical properties of a sparse, ionized gas sitting at a certain temperature and density, rather than from any kind of directed signal or externally imposed source. It is not, in other words, a message, a beacon, or anything remotely resembling communication. It is closer to the electromagnetic equivalent of background noise, the natural hum any plasma at this particular density and temperature would be expected to produce, simply detected directly, for the first time, by an instrument finally sitting far enough away to measure it cleanly. If you have found this as interesting as I did while researching it, drop a comment letting me know, because it genuinely helps me figure out what other space stories are worth covering next. It's worth pausing here to address something directly, because a title almost identical to this one has also been used to spread genuinely misleading claims online. In the years since the original 2021 announcement, a number of videos and articles have framed this discovery using language suggesting NASA detected an alien signal, a message from another civilization, or some kind of deliberate transmission aimed at our solar system. None of that is accurate, and it's worth being direct about why. The researchers who identified this emission were explicit in their own published paper and in public comments afterward that the leading physical explanation involves the ordinary thermal behavior of electrons in a sparse plasma, a completely natural process that would be expected to occur in this kind of environment regardless of whether anyone was out there listening for it. It carries no encoded pattern, no repeating structure, and no characteristics that any credentialed radio astronomer studying it has ever described as suggestive of an artificial or intelligent origin. It is a real, fascinating, and genuinely useful scientific measurement. It is not a message. Now, to Voyager 2's actual role in this story, because it deserves real attention, even if it isn't the one that generated the original viral headlines back in 2021. Voyager 2 carries its own plasma wave instrument, and has been transmitting from interstellar space since its own heliopause crossing in 2018. There is, however, one genuinely important difference between the two spacecraft that makes Voyager 2's data uniquely valuable in its own right. Voyager 1's dedicated plasma spectrometer, the instrument built specifically to directly measure plasma density and composition, failed decades ago, forcing scientists to rely entirely on the indirect oscillation-based listening technique used to identify both the original 2013 burst and the 2021 persistent hum. Voyager 2's equivalent plasma spectrometer, remarkably, still works. That means Voyager 2 can measure the density of the interstellar plasma surrounding it directly, immediately, and independently, without needing to rely on detecting a specific oscillation frequency at all. According to research analyzing data from both spacecraft together, that independent direct measurement from Voyager 2 has proven enormously valuable precisely because it lets scientists cross-check everything Voyager 1 can only measure indirectly. Since Voyager 2 crossed the heliopause at a completely different location, years apart from Voyager 1 and pointed in a different direction through the sky, researchers have been able to compare readings from both spacecraft to understand not just what the interstellar medium looks like at a single point, but how conditions vary across different regions of the space immediately surrounding our solar system. According to ongoing research tracking disturbances in this region, Voyager 2 has independently detected its own set of pressure fronts and shocks moving through the local interstellar medium since its crossing, some of which line up with similar disturbances Voyager 1 recorded from its own separate vantage point, and some of which do not, giving researchers genuinely valuable insight into how uniform or how uneven this region of space actually is. That comparison work has become one of the more active areas of ongoing Voyager research in recent years. According to published analysis combining measurements from both spacecraft, Voyager 1 has recorded multiple major shocks and pressure fronts moving through the interstellar medium surrounding it since crossing the heliopause, driven largely by what researchers call global merged interaction regions. Essentially, large-scale disturbances built up from multiple individual bursts of solar activity merging together as they travel outward through the solar wind and eventually slam into the boundary of the heliosphere from the inside. Voyager 2, sitting in a different part of the sky, has recorded its own independent set of pressure fronts and at least one shock of its own since its own crossing. Some of these events appear to correspond to the same underlying solar activity detected by Voyager 1, arriving at each spacecraft's very different location after traveling outward through different paths, while others appear unique to one spacecraft's specific vantage point. Untangling exactly which disturbances are shared, solar-driven events reaching both spacecraft eventually, and which are more localized features, specific to one particular region of the local interstellar medium, remains an active area of ongoing analysis, and it's precisely the kind of question that becomes answerable only because two independent spacecraft happen to be reporting back from two separate locations at once. Picture, for a moment, exactly what it would mean to actually listen to this signal, because researchers have made recordings of it public, and the experience is stranger than most people expect. Because the raw frequency involved sits outside the range of normal human hearing, scientists shift the recorded data into an audible range before releasing it. What results is not a dramatic, otherworldly sound at all. It's an almost eerily calm, steady, low tone, closer to a gentle static drone than anything resembling a voice, a melody, or a signal in the way science fiction has trained most people to imagine. There is no rhythm to it, no pattern that changes meaningfully from moment to moment, just a continuous, quiet hum generated by electrons gently vibrating in some of the emptiest, coldest material that exists anywhere in our immediate cosmic neighborhood, recorded by an instrument sitting more than 14 billion miles from the room you're sitting in right now. There's something worth sitting with in just how quiet and unremarkable that recording actually sounds, given the sheer scale of what it represents. This is not a signal captured from a nearby laboratory experiment or a controlled setting here on Earth. It is the sound, translated into a range human ears can process, of the actual physical material that fills the space between our solar system and the nearest other stars, gathered by a spacecraft that has been traveling continuously since 1977, older than most of the astronomers currently analyzing its data. Every recording of that hum represents plasma physics happening in real time, roughly a full day's travel away at the speed of light, translated patiently across that entire distance into something a person sitting at a laptop can actually press play on. It's worth taking a moment to explain why researchers care so deeply about something that, on its surface, sounds like little more than background noise. According to Ocker and her colleagues, having a continuous, reliable way to measure interstellar plasma density matters enormously for understanding how our sun's heliosphere, the enormous protective bubble carved out by the solar wind, interacts with the surrounding galaxy over time. That bubble isn't static. It expands and contracts in response to the sun's roughly 11-year activity cycle, and understanding exactly how the density of the surrounding interstellar medium responds to those changes helps researchers build far more accurate models of the boundary that separates our entire solar system from the rest of the galaxy. Every additional data point either Voyager sends back, whether from a dramatic shock-triggered burst or from this quiet, continuous hum, feeds directly into that broader effort. It's worth spelling out exactly why that breathing motion matters so much to researchers, and not just to Voyager specifically. Every planet in our solar system, including Earth, sits inside that same protective bubble, shielded to varying degrees from a portion of the high-energy galactic cosmic radiation that fills the wider galaxy. As the heliosphere expands and contracts along with the sun's activity cycle, the amount of that shielding effect changes correspondingly, a genuinely relevant factor for understanding radiation exposure for any future long-duration human spaceflight beyond Earth's own magnetic field. Having two independent spacecraft sitting in different locations along the boundary of that bubble, continuously reporting back on the density and behavior of the material just outside it, gives researchers a genuinely valuable, real-time way to track exactly how that protective structure is behaving, rather than relying entirely on theoretical models built without any direct measurements at all. There's also a more recent thread to this story worth including, because both spacecraft have continued generating fresh data on this exact topic well past that original 2021 announcement. Researchers studying the very local interstellar medium have continued tracking how conditions around both spacecraft have evolved in the years since, including a notable magnetic field disturbance Voyager 1 detected beginning in 2020, sometimes referred to in published research as a magnetic hump, which built gradually before reaching its peak roughly a year and a half later, and then settled into a period of unusually strong, slowly varying magnetic field readings that persisted for years afterward. According to ongoing modeling work, combining data from both spacecraft, researchers are still actively working to fully explain the complete sequence of pressure fronts, shocks, and magnetic disturbances each spacecraft has recorded since crossing into interstellar space, treating each new data point as another piece of a still developing picture of exactly how our solar system's boundary interacts with the wider galaxy around it. It's also worth being honest about the ticking clock hanging over all of this research. Both Voyager spacecraft run on radioisotope thermoelectric generators, nuclear power sources that have been steadily declining since launch in 1977, and current estimates suggest their remaining instruments could lose enough power to stop operating entirely sometime around 2028, though the exact timeline remains uncertain and has already been pushed back further than some earlier predictions through careful power management by mission engineers. Every additional recording of this interstellar hum from either spacecraft adds to what will eventually become a fixed, unrepeatable dataset, since no other spacecraft currently exists anywhere near this region of space, and no replacement mission capable of reaching it is currently funded or in development. So what does all of this actually add up to? There genuinely is a real physical frequency being measured from outside our solar system, a faint, steady hum generated by the natural thermal vibration of electrons in the interstellar plasma itself, confirmed through published peer-reviewed research and even released publicly as an actual audio recording anyone can listen to today. That discovery, though, first came from Voyager 1, not Voyager 2, back in 2021, building on an even earlier detection from 2013. Voyager 2's real contribution to this story is quieter, but genuinely valuable in its own right, an independent, directly measured confirmation of the same interstellar environment, gathered using a plasma instrument that never failed the way Voyager 1's did, from a completely different location in the sky. Together, both spacecraft have given scientists something no single instrument could have provided alone: two independent, cross-checked windows into a region of space that, before either Voyager reached it, existed only in theoretical models, rather than in any real measured data at all. It's worth reflecting, too, on why getting a small detail, like which spacecraft made which discovery, actually matters, beyond simple accuracy for its own sake. Voyager 1 and Voyager 2 are not identical, interchangeable instruments. They carry different working equipment, they crossed into interstellar space years apart, and they currently sit in different locations relative to the Sun, each one offering scientists a genuinely distinct vantage point on the same broader question. Collapsing both spacecraft into a single interchangeable idea of Voyager erases exactly the kind of detail that makes this research so valuable in the first place. The fact that we have not one, but two independent instruments, each with its own particular strengths and limitations, quietly reporting back from two separate points along the edge of our entire solar system. Getting that distinction right isn't pedantry. It's the difference between understanding what was actually measured and simply repeating a headline that sounds impressive without knowing what it's actually describing. Here's the detail worth sitting with as this video wraps up. Somewhere out past 14 billion miles in one direction and roughly 12 billion miles in another, two machines built more than a decade before the first personal computer ever reached a home are still quietly reporting back on the exact physical texture of the space between our star and the rest of the galaxy. Neither one is picking up a message. Neither one has found anything resembling a signal aimed at us. What they've found is something arguably more remarkable than that. Direct, physical measured proof that the seemingly empty gulf between stars is not silent at all, and that two aging spacecraft, launched during the Ford administration, are still the only instruments in human history capable of listening closely enough to hear it. If stories like this one, grounded in real published research rather than exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications, because both Voyager spacecraft are still out there, still transmitting, and there is a real chance the next signal that reaches Earth adds another genuinely fascinating piece to the sound of the space between the stars. Thanks for watching, and I will see you in the next one.